Okay, so let's go over our reactions of carboxylic acids. So just two things to keep in mind. We're going to need acidic conditions for these, otherwise we're going to form the carboxylate ion, which is highly unreactive. And then also you don't want to use a negative charged nucleophile because it's actually just going to grab that OH, this H right here. Think this is a carboxylic acid. This is an acid. It wants to donate that proton, and it'd be really easy for a nucleophile to just grab this. This is a very acidic proton. See, it's with both these oxygens on here. So, okay, let's go ahead and jump right into the reactions. Okay, so you have a carboxylic acid here. Go ahead and just write that out. And let's just react it with an alcohol as normal. Remember, we need acidic conditions, so we can add acid, HCl. And it's really the same premise as esters or acyl halides. We can just replace this group here with our nucleophile here, as long as we're getting rid of an H. So that would give us OCH3 and ester. The side product would be H2O. Hopefully you can visualize that. That's coming from this whole part right here and one of these, or this H that was hanging off that oxygen there. Okay. Let's go and do another reaction. Got a carboxylic acid here, and we're going to react it with ethanol, and remember it's got to be in acidic conditions because we don't want that carboxylate ion to form, or else the nucleophile is not even going to attack. Like I said, don't get confused by all this stuff over here. That's really just an R group. It's just going to stay the same. What's reacting is, this site right there. So, keeping that the same. Also going to have that there, and we're just adding on our ethanol here. Starting, you always add it at the electronegative atom there. There you have it. 1, 2 carbons, 1, 2 carbons right there. And that is your ester again. So hopefully that helps just visualize that. And again, the side product would be H2O, coming from this here and this hydrogen there. Okay, so let's go ahead and react a carboxylic acid with an amine. Now with amines, this is our amine right here. I just drew out, we need heat to go with these. It would be, I believe the exact temperature is 225 degrees Celsius. So that we need all that heat if we want it to properly add to, just like our other reactions with acyl halides or esters, to get your amide. Now, amide this. So we need the heat, if you want to think about it, is because if you do just, if you do it without the heat, this is an acid, and NH2CH3 is a base. So instead of having a normal substitution reaction, you're going to have an acid-base reaction. What happens in those is, the acid wants to donate its proton over there, so that would give us, R like this with O minus, and this is actually a salt here, NH3 now instead of NH2, CH3, and this has a positive charge there, which is actually a salt there. And then so in your next step you add heat, 125 degrees Celsius, and that's going to, you're going to, lose your water there. Take out your two H's from here, and then your O is coming from right there. And then that's just going to give you your product. That's kind of the mechanism for how that works. But in reality, this kind of leads you up to our next reaction we're going to cover here. Is 225 degrees Celsius. That's big warm right there. That's really hot if you think about that. That might not be realistic to heat that up to that temperature. So a lot of times what we do with carboxylic acids, which may just be a better reaction, more relevant with your materials in the lab or whatever, but so we convert it to an acyl halide. So we do that using Socl, SOCl2 there. And all that's going to do is convert us to an acyl halide, which, if we remember, acyl halides are very reactive. They'll react with just about anything. So from there, you don't have to worry about doing these extra steps like adding a bunch of heat. Because now you got your acyl halide that's going to react with just about anything. So that's really it for our reactions there. I guess we can. So if you want to just try to visualize this out right quick, this is why we would not use a negative charged base if we had an OH minus like this. Instead of wanting to attack right here, does not want to do that. It would actually much rather just grab this very acidic proton right here, and then we have our OH minus, our carboxylate ion right here. And if we should know that this is actually very unreactive, towards a nucleophile. Think a nucleophile has a negative charge generally, or at least partially negative charge. It doesn't want to attack anything that has a negative charge in there. Opposites attract. Negative likes a positive charge, if anything. But so I hope that helps visualize that. As you can see with these reactions here, we're just adding on our whatever we're adding in place of this OH and carboxylate and the carboxylic acid. So that's really the premise of reactions with carboxylic acids.